Hello, everyone. Can somebody please use Q&A to let me know that if you can hear me? So you guys cannot hear me? Okay. Great. So there is only one announcement that you probably know. The quizzes have been graded and the result is available on Learn. Next quiz will be published again on Monday. And the deadline for P1, sorry, for P2 is also coming. So if you haven't started yet, definitely get started. Okay, so let's get started with the lecture. And let me get my own video. Okay, so to just recap, we talked about, we started this lecture about 3 lectures ago. I mean, this topic. We started by talking about the implementation of a multi-threaded kernel. From there, we talked about how you can create a thread, how you can context switch between threads. Then, once we were done with all of that, we started talking about synchronization. We spent some time going through multiple implementations of mutex. We started with Uniprocessor, and then we talked about multiprocessor implementations. Going forward, when we talk about multiprocessor scheduling, we'll see 2 other implementations of mutexes. But then we started, we went on to semaphores. We talked about them. That was just a recap. And then we saw how they could be implemented. Then we discussed why they shouldn't be used. They should be known. You should know them, but it's better for your code not to use them. And then we did a recap on monitors. We defined them. We saw a particular example, producer-consumer, and a bounded buffer. Now, the last thing we talked about last time was how to use condition variables in our code. So the pattern we saw in the producer-consumer code was something like this. So we had a while loop, and then we would check the condition that we want to wait on. So let's say if we are a consumer and we want to consume an item, so we want to wait as long as the queue is empty. Now, the code that you saw had a while loop. So in a while, we check the condition, and if the queue is empty, we wait on that condition variable. To just emphasize something here, we're passing mutex to wait. So this function, which we will see the implementation of, is going to release this mutex and then put this thread to sleep by basically calling thread switch at some point. And then at some point, it will wake up after that line, after the thread switch. The first thing this function has to do before exiting is to acquire the mutex again, to lock that mutex again. So let's say an item is put on the queue and we are the one that gets the signal. We wake up. Now, the first thing the wait has to do is to acquire this mutex before exiting. Now, let's say the mutex is already locked by some other thread. In that case, we're going to go back to sleep, but this one not on this queue, but on the mutex's queue, because we wanted to acquire the mutex, which was locked. So we're going to wait for mutex. Then let's say at some point the mutex gets released too, unlocked, and we wake up to acquire it. We lock the mutex, and then we exit this wait. The moment we exit this wait, we're going to go back to this while and check this condition again. Now, you might say, why do I need to check this condition again? I once checked it and it was empty and I woke up. So it means that somebody put something on the queue. So I should be able to get it. And the answer is, well, it depends. It depends on what kind of monitor you're using. There are two types of monitors, Mesa and Hoare monitors. So with Mesa monitors, which are, by the way, the ones that are being implemented widely, there are not many Hoare implementation. Most of the implementations are Mesa implementation. With those, you always have to wait. And the reason is exactly because of this mutex that you have to acquire again. Let's say that you wake up in this wait and you don't have the mutex. That means that somebody else has that mutex. That somebody else that has the mutex could be another consumer that just came. So this new consumer who just came acquired the mutex before you, and they checked the queue and it wasn't empty, so they consumed the item. So now that you woke up and after them you got the mutex, you have to check it again, because it could be that the previous one who got the mutex consumed that item that was put there. And that is with Mesa. We'll see how it is implemented with Hoare. So with Hoare, you can just go with if, but with Mesa, you should definitely go with while. And because all the mainstream programming languages, they all implement Mesa, so you always have to go with while. You should never go with if. Okay, so let's see an example how Hoare monitors work. This is when you can actually use if. So let's say you acquire the mutex, you lock the mutex, and this is a producer. Let's say the producer acquires the lock and puts an item and then signals. This signal, the moment it signals, it's going to give the mutex and the CPU to the one who wakes up. So it basically, in an atomic way, releases the mutex and yields the CPU. Let's say we're implementing it on a Uniprocessor, and gives both of them to the one who just woke up. So in this case, well, you don't need to have a while here, because you just got the mutex. You don't need to fight for the mutex, and you just got the CPU. So this guy got blocked at this point when it's signaled, and now you continue. Once you're done, you go back to the one who signaled you. And this is how it works with Hoare Monitor. Now let's see this in the context of Mesa. With Mesa monitors, this is the producer. Let's say it signals. What it does, this signal, all it does, it puts one waiting thread, one of the threads that were waiting on this MTCV, on the ready queue. It's kind of like thread create, where you just create a ready thread and then you move on. It's non-blocking. You don't get blocked there. You just put this thread on a ready queue and you continue. Once you're done, once you finish your execution, probably could the scheduler could pick this guy, or it could actually pick some other thread. There is no guarantee who will run next. But at some point, because this is already now, this thread is ready, it will be picked up. So the first thing it has to do is it has to acquire the mutex. Let's say mutex is empty. Then it has to actually check this while. And because of this step in the middle, where scheduler chooses who runs, you have no certainty that the queue is still empty. That's why you have to check it in a while. Yeah, so if you change this to if instead of while with Mesa monitors, let's see what happens. Let's see one example where instead of while, we use if. So in this example, I'm running the same producer-consumer code. Now, thread 1 is a consumer. Thread 2, which we will see, is a producer. And then I have a thread 3, which is also a consumer. Now, let's talk about these on top. I have the queue. This is basically the buffer that the producer and consumer are using. This is my monitor. The monitor has a mutex, which initially is unlocked, and it has an empty CB queue. It also has a producer queue, but because it's not a focus of this example, I don't have it. So I just have the empty CV queue, which is initially null. And then there is only one CPU here for simplicity. And let's say that CPU is running T1. And it has a ready queue, which is null. Nobody is ready. So hopefully the setup makes sense. Now let's start running T1. So, okay, at this point, we lock the mutex. So you can see that inside the monitor now, the mutex is locked. Now, we check the queue is empty. Nothing is in the queue. So we're going to wait. So at this point, we add ourselves to T1, and we unlock the monitor. So monitor is unlocked. T1 is now on the empty CV, and nobody is running. So T1, the state has changed to waiting. It's not running anymore. So it yielded. Now, let's say T2 comes in and starts running. This T2 is a producer. Now it acquires the lock. So I have the lock. So the lock is the mutex is locked. And at some point, it produces an item. So it puts an item on the queue. And once the item is on the queue, it's going to signal. OK, what does this signal do? Now, let's look at everything here. The signal has removed T1 from empty CV and put it on the ready queue. So now T1 is ready. The mutex is still locked, and T2 is running. And there is one item on the queue. So yeah. Now let's say T3 comes in at this point. Because T2 is running, T3 also goes to the back of the ready queue. Now T2 terminates. T2 is done. Now scheduler has to pick, because there are two tasks on two threads on the ready queue. Let's say the scheduler picks T3. So now T3 is running, and T1 is on the ready queue. So what does T3 do? T3 acquires the lock. Now the mutex is locked. it checks the queue. There is one item on the queue, so there's no reason to wait. So it consumes that item, and it terminates. Now scheduler has to pick again. Scheduler has another thread to run, and that would be T1. So it starts running T1. T1 here at this point acquires the lock, so the mutex is locked. But it's going to continue. So the moment it gets out of this wait, after it acquires the lock and it wants to get out of this wait, it assumes that the queue is no longer empty. It's not going to check again because I don't have the while. So here comes the error. So now I get an error. And that is the exact reason why you should always use while here. So I have to mention this here. I looked at your notes from ECE 252, and it feels like the implementation that was discussed was the Hoare implementation. So the code that I saw there, they only had if. So this is a big difference here from ECE 252 to ECE 350. And that is basically, we're considering only Mesa implementations, unless otherwise stated. So if I don't state anything, then I'm just focusing on Mesa implementation, which means that you have to use while. Okay. Now, there are other reasons for you to use while in Mesa implementation, other than the one that I just showed you, that example. This is from Java user manual. And if you read this, this is how Java implemented monitors. They say that when waiting upon a condition, a spurious wake up is permitted to occur. Basically, what that means is you could wake up for no reason. Even if nobody has signaled, you could potentially wake up. That's how they implemented it. I don't know why, but that's the implementation. So you wake up without anybody's signal, and if you don't have that while to check your condition again, you're going to assume that the item is put on the queue, and then you go ahead. And that is a wrong assumption. So this is another reason for you to always use while instead of if. Okay, now let's do a comparison between condition variables and semaphores. As we mentioned, semaphores have memory, so they memorize how many times P and V have been called, whereas CV does not have memory in terms of the signal. So signals and broadcasts get lost if nobody is waiting. I repeat again, this is a very important point that always is asked in quizzes and exams. Signals and broadcasts get lost when there is nobody waiting. So we don't memorize them. So if nobody is waiting and you signal and then somebody else comes and waits, that latecomer is not going to use the signal that was sent before it comes to the waiting queue. And that's basically different from V in semaphores. In that case, we are actually memorizing it. Generally speaking, as I mentioned numerous times, monitors are better. They give you better readability to your code. But there are examples where you might want to use semaphores. And this is basically one of the reasons that semaphores appear a lot in Linux kernel. This is one example I'm going to give you. This is one example where it makes more sense to have semaphores rather than monitors. So let's say that we have a shared memory that is read and written by by the kernel and by the hardware. So hardware controller is going to write to this memory, and then kernel device drivers or kernel tasks are going to read from this memory. So this memory is shared between hardware and kernel. Now, hardware cannot use the software mutexes because hardware doesn't know how to use them. It just can read or write characters to a buffer. That's it. It can't acquire it cannot call functions and such. So no mutexes in this context. I got a question. What's the advantage of Mesa versus Hoare? Okay, that's a very good question. Let me publish this question. So the advantage of Mesa over Hoare is ease of implementation. So in order for you to, it feels like Hoare, the Hoare implementation is very strict in how signals and broadcasts should be implemented. It has to be atomic. So you have to suspend the signaler, you have to pick the one who gets the signal, and then you have to atomically transfer control to that newly awakened thread. Whereas in Mesa, it's easy to implement. You just make that thread ready and then leave the rest of it to future randomness. So that the one who just got waken up, it can or it cannot acquire the mutex, and it can or it cannot get the item that was produced or the condition that was resolved. Now, again, it's just ease of implementation, but then ease of implementation means a lot of randomness and confusion potentially for the programmers. So implementation-wise, Mesa is much easier to implement. Reasoning about a code, Hoare is much easier to reason about what happens in your code, whereas Mesa has a lot of randomness. That was a good question. Okay, so going back to the example we had. So let's say that kernel thread, let's say the device driver or whatever, checks for data in that buffer, and let's say it doesn't find the data, and now it wants to wait until data is ready in that buffer that is shared between the hardware and the kernel. Now, if this waiting happens with a monitor, with a condition variable, then at some point the hardware code somehow has to signal this guy, right? Now, if because this signal is not the one who is going to signal does not hold the mutex, so there is no mutual exclusion in terms of the internals of this monitor. So this signal could be sent right before the kernel thread goes to sleep. And because there is no mutual exclusion in terms of how we're implementing the way we're implementing this code, so the signal could get lost. Now, this has a name. It's called naked notify. Basically, you're not notifying, you're signaling without holding the lock. And well, that is not good. Initially, when I talked about monitors, I said, don't do this. Always use signals and broadcast and all of that while you're holding the mutex. In this context, it's not possible for the hardware to hold the mutex. So it could signal without holding the mutex, and that signal gets lost. Now, and again, the reason that it cannot hold the mutex, I take it back. The reason it cannot hold the mutex is what we talked about. Let's say this is an interrupt handler, and we talked about the fact that the interrupt handler cannot hold the mutex, cannot use the mutex because it cannot basically be interrupted sorry, because it cannot, when somebody else has that mutex, the handler cannot be suspended. Because it cannot be suspended, it cannot use the mutex. So without mutex, you can signal, right, inside your interrupt handler. I think I confuse everyone when I said something about code. Let's say the hardware that I'm talking about here is basically, what I mean is interrupt handler. So let's say there is a kernel thread, which might be the device driver, and then the hardware is basically using the interrupt handler code. So there's an interrupt handler code, and then there you have your kernel thread. Now the interrupt handler cannot use the mutex. We talked about that. So now let's say the kernel thread wants to wait, and then here the interrupt handler is going to use the signal without holding the mutex, because it cannot hold the mutex. Now this causes problem, as I mentioned. The problem that could happen is that the kernel, before it puts itself to sleep, before adding itself to the waiting queue, this signal could come and then get lost. And then kernel puts itself to sleep and then waits forever. The way to deal with it is just to use semaphores instead. Instead of calling signal, this interrupt handler can call V, and that gets memorized. So no matter when this kernel thread goes to sleep, eventually it's going to see this V. Either it sees the V after going to sleep, or before going to sleep, the V is issued, it goes to sleep, and then it sees that V. Got a question. So are we talking about a condition variable or semaphore? So again, I think I confused everyone. So I'm going to go through this example one more time. So we're talking, let me just change the slide on the on air with interrupt handler. Okay. Now I think it makes sense. Sorry for that. Was a okay. So I got another quick question. Do you update the slides on the course website after you make these changes? Yes. So the slides are being uploaded on GitHub. So I actually change it as I make these changes. I upload the changes on GitHub, so you can see all the previous updates. If you have downloaded an slide previously, you can see ever since what has changed. I usually, when I commit, I say what has been changed. Okay, sorry about that. So let's go back to this example. Let's say that we have a shared memory that is used concurrently by the interrupt handler and a kernel thread. So now this should make sense. Now we talked about this fact that interrupt handler cannot use the mutex because it could cause, because they are not basically suspendable. You cannot suspend an interrupt handler. Whereas with mutexes, you always have to suspend. If you want to acquire the mutex and you don't have it, you get suspended. Now, let's say the kernel thread checks for data and calls wait because there was no data there. If interrupt handler writes to the shared memory and calls signal, then we might have a problem because the interrupt handler did this without holding the mutex. Now, what that means is that this signal could be sent before the kernel thread is put to sleep and basically gets lost. So to avoid this, we can just use semaphores. So inside our interrupt handler, we can use semaphore. So semaphore calls, the interrupt handler calls V, and no matter where the kernel thread is, this V is memorized. And either the kernel thread goes to sleep after or before the V, it will see that V. So it gets resolved. Okay. I apologize for the updates that I had to make on air. Okay, but at least at this point it should be clear. Okay. So now let's look at implementations of condition variables. They're very similar to what we've seen. So the only state that the condition variable has is the waiting queue that it supports. And then it has three functions: wait, signal, and broadcast. Let's look at them. So this is wait. So all it does is it adds the thread that called wait to the waiting queue. It suspends that thread. And at this point, it actually acquires the lock. Okay, so 2 points to talk about. So where is this mutex freed? It gets freed here inside the suspend. If you go back and look at the scheduler suspend code, you will see that what this suspend does, it basically releases the mutex and then puts this TCB to sleep and context switches. Now, this is what I was talking about in wait. The moment before you get out of the wait, you have to lock the mutex again. So when you come back from suspend here, after you come back from suspend, you have to acquire the lock before you exit wait. So 3 lines of code, but a lot of important information. So we added ourselves to the waiting queue. We release the mutex, put ourselves to sleep. The first thing we do after we wake up is to lock the mutex. Now this is signal. When you signal, what do? Well, you just check the waiting queue. If there is if somebody is waiting, if the waiting queue is not empty, you remove them and you make them ready. That's it. That's all you do. And then you continue. You don't context switch or anything. You just make them ready. And the broadcast the same. So in broadcast, you basically, instead of just signaling one thread, you signal everyone. So you have while. So a question here. So if you look at this class condition variable, you don't see any spin lock for the CV. Why is that? We usually, if you go back to any of the other classes that we implemented, the scheduler, the mutex, the semaphore, they all had a spin lock. Whenever we would use the internal, we were updating the internal of that class, we would use that spin lock. But in this implementation, I don't have any spin lock. Can you think of a reason for this? I'm going to wait a little bit. Okay, so the reason is that it is assumed that all these functions are called when you hold the mutex. And that mutex will give you the mutual exclusion that you want with your implementation. So by default, if you follow the rules with condition variables, you basically have the mutual exclusion when you're calling any of these functions, because when you're calling any of these functions, you have to hold the mutex, and if you hold the mutex, we already have mutual exclusion. Okay, because only one thread can hold that mutex or can lock that mutex. Okay, so that's that. Now let's just try to implement condition variables using semaphores, just as an exercise. This is take one. To implement just wait. So what I'm doing here is that I unlock the mutex, I call P on my semaphore, and then once I come back from P, I lock the mutex again. So this P is gonna supposedly wait, and at some point it's gonna wake up, and I'm gonna just acquire the lock. So I got another question. How do we already have the lock? I just explained, right? So here, in this context, whenever you call wait, whenever you call signal, whenever you call broadcast, you have to hold mutex. So this condition variable is defined in the context of a monitor, and that monitor includes one mutex and bunch of condition variables. So that one mutex that you have in your monitor, that you actually pass through this wait here, where you're calling wait, you pass the mutex, it means that you have already locked that mutex. So if you have already locked that mutex, and because this condition variable, all of these functions are called whenever a thread holds a mutex or has locked a mutex, then you already only have one thread at a time executing any of these functions. So you already have mutual exclusion with these functions. That's basically why we were saying every time you want to use these functions, you have to have locked the mutex. Okay. Question, but then in wait, why is the mutex locked at the end if we already have it? Well, here is where we want to, when we called wait, we had it. Now we want the invariant to be when we come out of wait, also we have it. So before we get out of wait, we try to lock the mutex again. So the invariant is whenever you call wait, you should have locked the mutex, and that's what this implementation actually does. Now the assumption is when you actually exit wait, you should again have the lock, because when you called it, you had it. That's why we acquire the mutex again, or we try to lock it again, so that we have this invariant. Entering wait, we had locked the mutex. Exiting the wait, we still have to have the lock. Okay. Now, yeah. So this is the first try to implement, and let's look at signal, and for signal use V. Now, what's wrong with this implementation? The one thing that is wrong with this implementation is that we're using semaphore V, and that has memory. So this implementation of signal has memory. So if this signal is called before this wait, then we memorize, and the one that waits will use this V here in its P, which is not what we want. Okay, so let's try another implementation. This one is kind of like a pseudocode. We haven't changed the wait, it's going to be the same. But for the signal, let's say if Semaphore's queue is not empty then call V. If the semaphore's queue is empty, then don't call V. What about this implementation? Well, there are two bad things about it. The first one is that we don't see the internal of a semaphore. All we see is the value of semaphore, so we don't have access to the queue of a semaphore. The other problem with this is also the fact that it's not atomic. So again, what if we check here, there was nobody, but then at this point before we execute V, somebody goes and adds itself to the queue. So then this V will disappear because it's from this checking to this V, we don't have any notion that would guarantee atomicity. So this V could get lost. Now, this is take 3, and this is the implementation. And the idea behind this one is that let's have a separate semaphore for each waiting thread, and then put these semaphores in an ordered queue to resolve the fact that we want to somehow check if somebody's already in the queue of the semaphore. That we can't do, but we can actually create a waiting queue of semaphores. Let's look at it. So this is the wait. So whoever calls wait, we're going to create a new semaphore for it. Then we're going to add this semaphore to a queue. Hopefully at this point we actually have the mutex. So this is done atomically because we had the mutex. We haven't yet unlocked the mutex. So when we add ourselves, nobody else is dealing with this queue. So after we add ourselves here, we unlock and we call P on our semaphore. Now let's look at signal. Now we have a queue here. Again, this signal hopefully is called when the mutex is locked. So I have atomicity. So I check if this queue is empty. And if not, then I can remove some semaphore from this and call V on that one semaphore and get done with it. So this is an implementation that we can actually use. So let's say instead of implementing condition variable, let's say you have an implementation of semaphores, you don't want to, again, go and implement condition variables from scratch. You can now use your semaphore implementation to implement your condition variable. Okay, this is a summary of this lecture. So we talked about hardware atomic primitives, like test and set, like disabling interrupts, like load and store, and all of that. We also defined the lock variable, and we saw how to implement mutexes. We talked the invariants that are important to implement and to maintain, one of which was when you disable interrupts, the first thread that starts running has to enable them. And then in all our implementations, we have to be super careful not to waste CPU cycles. We always have to avoid busy waiting if possible. So that's why we had multiple attempts to implement mutexes. Okay, so I'm going to give you 2 minutes to rest, 3 minutes to rest while I get the lecture 4 ready. So have some rest and then we'll start from lecture 4. Okay, I got a bunch of questions. Oh no, these are old ones. Okay, so 1 more minute and then I'll get started. I got a question. Where is this slide deck? On the website. You probably have to refresh. Okay. Let's get started. In this lecture, we're going to start talking about uniprocessor scheduling. There'll be 3 lectures on scheduling. So the first one of which is this one. We will start with uniprocessor scheduling. Then we switch to multiprocessor scheduling. And then once we're done with both of them, we start talking about real-time systems and how you can schedule tasks for those systems. So the outline of this lecture is as follows. We will start with a very brief history of scheduling and why it's important, why it's interesting. Then we talk about some definitions, and then we start basically seeing a bunch of scheduling policies. A bit of history. So this is a quote from a very famous Linux creator, Linus. In 2001, he said that, and you have to realize that there are not very many things that have aged as well as the scheduler, which is just another proof that scheduling is easy. So this is around 2001. At that point, people considered scheduling as a solved problem. Now, here comes 2004, where Dinard scaling fails or ends, and we start getting into a new era of multiprocessors. And that basically renewed interest in scheduling, because before that, most of the schedulers and most of the scheduling policies were directed and focused on uniprocessors, which is actually the focus of this lecture. But then when we moved to the multiprocessor era and all the nitty-gritty of it, people started seeing that, okay, we need new schedulers, we need new policies. At some point, energy efficiency also became an issue and had to be taken care of. So years later, about a decade later, more than a decade later, in 2016, a paper was published pointing out numerous bugs and inefficiencies in Linux kernel. In some cases, there were workloads that got slow, that would experience the slowdown of all the way to 138x because of those bugs. So, and this is like 2016. It's you have to go back to this code from 2001 and wonder if really scheduling is easy and if it's really solved. So it's definitely not, and we'll see it. And it's really an interesting topic. It got again renewed after the specialized hardware came into picture. So after this multiprocessor era, we now have already started another era, which is a specialized hardware. And people have started again looking at the scheduling because scheduling these new hardware requires new policies and new thoughts that have to go into this. So this is an area that I do research, and if any of you guys are interested in any of the topics that actually we've talked, definitely shoot me an email. We can definitely discuss research opportunities if you're interested in these. Okay, so hopefully this gives you a perspective on scheduling and the importance of it, and why it's interesting and exciting. Let's get it started with it. I'm starting with a bunch of definitions, which would set the tone for what comes forward, what comes next. So these are a bunch of words or phrases that I'm going to define. Task, thread, process, job. So I'm going to use all of them interchangeably. What I mean by them is that they're a unit of work that has to be scheduled. Depending on the context, it could be a mouse click, it could be a web request, it could be a shell command, it could be an entire thread. So we'll see, like, you have to, think about it in the context that it's being discussed. But what it means is that it's just a unit of work that could be scheduled and use the processor. So this is basically what is waiting in the waiting queue of a CPU to be scheduled, whatever that is, thread, process, job, task, we're going to call it. And then we talk about workload. Workload includes a bunch of tasks. So it's a set of tasks that are given to a scheduler to schedule. Now, what is a scheduling algorithm? Basically, it's an algorithm that generates a schedule that tells you, given the workload, given the set of tasks, how they're going to be scheduled, which one is going to run first, which one is going to run next, and so on and so forth. Overhead is basically the amount of extra work that the scheduler does, because whatever a scheduler does is not towards finishing basically those workloads, those tasks. So whatever we do to schedule them, to give them CPU, it's kind of like an overhead. So you want to minimize the overhead. Then you have preemptive schedulers. These are the schedulers that could take away CPU from a running task. You have work-conserving schedulers. These are the schedulers that would assign an idle CPU to a task if there are tasks. So if CPU is idle and you have a work-conserving scheduler, these two facts mean that there are no tasks in the ready queue. Because if there was a task in the ready queue, it should get scheduled and use the CPU. So we're not going to leave the CPU underutilized or not used if we have a work-conserving scheduler. Now here's a question, an interesting one. So if you have non-preemptive schedulers, if your scheduler cannot preempt tasks, then work conserving is not always a good thing. Why? So I'm going to pause a little bit to give you some time to think about this question. Okay, here is an answer, one example. Let's say CPU becomes idle and I have a low priority task in the ready queue. But this low priority task is a long one. Now, if I don't have preemption, the moment I start this low priority task, I have to wait for it to finish. Now, if I do so, and then only a second after I start running this low priority task, a high priority task comes, then this high priority task has to wait for this low priority task to finish. And that might not be something that I want. So if had I had the knowledge that this high priority task is going to come, I would have waited, basically wasting CPU time for the high priority task to come and then give the CPU to that high priority. So in that case, if I don't have non-preemption, then I probably want to wait and basically waste CPU, not allocating CPU time to any other task, even if I have them for, let's say in this example, a high priority task to come and start running. Okay, so in this lecture, unless otherwise stated, we're going to just focus on preemptive and work conserving schedulers. To recall, this was basically the state of a system, a working system. So you have a bunch of queues, bunch of waiting queues, and a ready queue if you have a uniprocessor. So we're going to focus on uniprocessor, as I mentioned in this case. So you have only one CPU, it has a ready queue, and you have a bunch of other queues. Let's say for you know, a thread that has joined on its children threads or other threads, or I/O devices that have their own waiting queues. So you have a bunch of queues, right? Now, many of these queues are controlled by the operating system. The most important one that is the focus of this lecture is the ready queue. But whatever we're going to talk about, you can use them in other queues that you might have in your system. You can use any of the scheduling policies that we talk about and we discussed in this lecture. Okay. So let's say we're running a thread. In reality, most of the time, the thread that we're running or a process that we're running has CPU and I/O bursts. So if, let's say, the execution comes from top, you're going to execute a bunch of instructions, do multiplications, sums, and whatever that be. And then at some point, you're going to wait on I/O. You do an I/O, you wait for it. Once it's done, you again do a bunch of instructions. You have a CPU burst, and then you get an I/O burst. You have CPU burst, you have I/O burst. Now, this is basically a figure that summarizes this behavior in terms of the duration of CPU bursts. So in this graph on the x-axis, I have the burst duration, how long each one of these CPU bursts take. And on the y-axis, I have the frequency. And as you can see, short bursts are very frequent. And really, really long bursts are not that frequent. So this should give us some idea that most of the scheduling decisions that we're going to make, we're going to be concerned with CPU bursts that are short. Now, after a thread comes out of I/O, it needs to be scheduled. So when we are making that scheduling decision, we're basically making a scheduling decision which thread is going to run its CPU burst until it hits another I/O and it's going to go to wait for I/O. And then come back, and then we want to make a decision on which CPU burst to service. And sometimes you might preempt a task in the middle of its CPU burst. So which is possible. So if you do so, then this task or this thread or this process is going to go back to the ready queue. It's not going to go and wait for IO or whatever because it hasn't reached its IO. Okay. So there are certain assumptions that we're going to make going forward in this lecture. We're going to make an assumption that each user of our system, if you have a multi-user system, each one of them is running one program or one process, and we're going to assume that each process has one thread, and we're going to assume that these processes and these programs are basically independent. There is no dependency between them. There are no synchronization. Basically, we're doing multi-processing instead of multi-threading. These are different processes that have no relationship whatsoever. They're not going to do pipelining. They're not going to share memory. They're just independent. Now, you might say, well, this is not real. This is not realistic. You're right. We're going to make these assumptions to make this problem simple to study it. Later on, when you master this simple question, then you can start relaxing some of these assumptions and see what you can do if you actually have those assumptions. Now, what are the things that we want from a scheduler? One of the most important things that a scheduler has to provide is good performance. Now, there are different definitions of performance. One definition is minimizing average response time. So what is actually a response time to begin with? Response time, this is a definition that will show up again and again in quizzes and all. So the response time of a task is when the task comes to the ready queue until it gets executed. So that's the response time. Now we want to minimize average response time, meaning that we want to minimize the average time that it takes for all the threads that come to the ready queue to start to finish. Okay? Now, one thing to pay attention to, and I'm saying this because of the quizzes and all, is that if you have a thread that has CPU burst, then IO burst, then CPU burst, then IO bursts, every time that it has a CPU, but every time it gets added to the, basically every time that it has a CPU burst, we calculate its response time from when it comes to the queue until it finishes and goes for its IO. And then we calculate this in our average. So we don't count the time that this task is going to spend in IO as part of our response time. So let's see if I can do this here. Let's say the task came here. It did some stuff, and then at this point it went to IO. So this is where it's doing IO, and then IO done. Now here is on the CPU side until another IO happens, and then again IO. So in this period, this is the period that I'm interested in terms of response time. And again, this is another response time for this task or for this thread. I'm not going to count this one for the response time of this thread. So I'm going to, every time it comes to the ready queue until it's done with its burst and goes for IO, this becomes the response time of this, the first part. And then this becomes the response time. So if I want to calculate average response time for this thread, I'm going to average these guys, how long they took from when it was ready until it went for a CPU burst. I'm not going to count this because at this point, this is out of our control. It's going to go to I/O and it's going to get served with I/O. So we're not going to count that. We're just going to focus on the times that it was under our control as a scheduler for CPU and see how much we made this CPU burst take. Okay. Now, we'll talk about this one. We'll talk about real-time tasks. So with those, we're not going to worry about average response time. We're going to talk about worst-case response time. So if you have real-time tasks with deadline, then you don't really care about average response time. All you care about is to meet all the deadlines. The other metric that you can consider when you're talking about performance is throughput. So what is throughput? Well, throughput is tasks per unit of time or threads per unit of time. Basically, it means how many tasks I executed every second, let's say, or how many CPU bursts I executed per unit of time. Now, throughput is related to average response time, but they're not identical. So there are cases where minimizing response time could lead to more context switching, which in turn would hurt throughput. So context switching is one overhead that you face when you're talking about scheduling. When you decide that it's somebody else's turn, you have to context switch, and context switching takes time. Now, if you constantly context switch between your threads, you incur a high cost for context switching. Now, this could hurt performance in terms of throughput, but it might give those threads that you're context switching between them a very good response time, right? So you're helping response time, but you're hurting throughput. So if you want, you can think of, if you want to maximize throughput, you have two parts to care about. One is you have to minimize overhead. If you have less overhead, that means that you're doing more work. The other thing is that you shouldn't leave your resources underutilized, because if a resource is underutilized, if you're not using your CPU, you're hurting your throughput because you're not doing any work. If you wish, throughput is basically work per second. So if you're not doing any work, then you're hurting throughput. I got a question. Why do we use task per time when task can be variable? Isn't instruction per time better? Yes, it's up to us how we define. It's basically unit of work per unit of time. If you care about instructions as unit of work, then you can focus on instruction per second. If you care about tasks, then tasks per second. Let's say if you have, for those of you who know something like MapReduce or any of these analytics, you know, graph analytics or whatever, like a streaming job, they actually have tasks. That's their unit. Although tasks could have different sizes, but at the end of the day, what you care about is how many tasks you you basically serve. Or for instance, if you have a web server, then the unit of work that you're doing is requests. So basically, in that case, your throughput becomes how many requests you respond to per unit of time. Okay, so this one is very important. I emphasize that minimizing response time does not necessarily maximize throughput. There are cases where you can minimize response time, but then hurt throughput. There are cases where this one is important, and I just pose it. It probably will show up in the exam somewhere. But there are cases where you can, by just shuffling through the tasks, the order of your tasks, you can get a better average response time without touching throughput. So throughput is not changed. So throughput remains as is. For the same set of tasks, for the same duration, you just change the order of your tasks and you get a better response time or average response time. Again, so throughput unchanged, average response time in one is better than the other one. So again, there are relationships between maximizing throughput and minimizing average response time, but they're not directly connected. Okay, the other important thing that we might want to consider is fairness. And this is an area that everybody deals with it differently. Some people throw it away. Some people don't care about fairness. All that is important to their systems is basically performance, which makes sense. But if you need to have or to guarantee some notion of fairness, then the most general way to look at it is that you need to treat your users in an equitable way. That is very general. Now you have to define what it means to be equitable. So there are different ways to define equitable. One is maybe what you mean is give them all equal CPU time. But is it really fair, this one? Maybe you have this task that doesn't need CPU. It does a lot of I/O. So if you give it CPU, it's not going to use it. So although you are being equal in the way that you're treating your tasks or your users, you're not really necessarily implementing fairness. Some other ways would be maybe minimizing the variance in worst case performance. Maybe all you care about is the performance of your tasks. So instead of looking at how much time they got on the CPU, you look at their performance. So as long as you get equal performance, whatever that performance metric is, throughput, average response time, whatever, so you're fine. So that's another way. There are others who, I don't know if I have it in my slide, but there are those who define fairness based on slowdown. So, and then how do you define a slowdown? Well, slowdown is defined usually by saying that if I get all the resources, I get, let's say, performance X. Now, I'm not going to get all the resources because I'm sharing this device with other tasks. So I'm not going to get performance X. As a result of the scheduling policy, I'm going to get performance Y. And this performance Y is worse than performance X because now I'm competing with others, whereas performance X was when I had all the resources. So if I now divide Y by X, this is a number less than 1. And this shows how much I experienced slowdown, how much my performance degraded. So some definitions actually try to equalize a slowdown, making sure that everybody sees the same amount of a slowdown. That's another one. I had done some work in the past where we looked at fairness in the context of envy freeness. So all I care about is, would I prefer your allocation to my own allocation? And if nobody prefers anybody else's allocation, or scheduling decisions that have been made for others, if I don't want to switch my position with someone else, then your system is fair. I think this is the way economists define fairness. Plus work conserving, the fact that because you could give everybody nothing, and then nobody wants to change their decisions because all of the decisions are the same. Nobody got anything, but then you wasted the resources. So as long as you don't waste resources and nobody wants to switch their positions with others, you have a fair system. And in my opinion, this is the most comprehensive definition, because again, you leave that to the tasks to decide what performance metric they care about, if it is a slowdown, if it is other performance metrics. All you ask them is, do you prefer this allocation to your own allocation? And if they say no, then that's good. So they are happy with their own allocation. And if everybody is happy with their allocation, then you have fairness. Okay. There are a bunch of things that have to be thought of very carefully when somebody is designing a system for fairness. So you want to care about your actual users. Are your actual users your programs, in the sense that is each program associated to one user, or do you have users who have multiple programs? If the unit of work is threads, then how are you defining the slowdown on? Because I could have my process create 100 threads, and then I have somebody else has another process with one thread. If a unit of fairness, or the definition of fairness, concerns threads, and it's gonna make an equal decision for all threads, then I'm gonna get 100 times more than what the other person is gonna get, because I have 100 times more threads that other process. So these are the things that you have to definitely be careful about. Okay, so how much time do I have? I basically have 1 minute. I think this is a good place to end this lecture. I'm not going to start with first come first serve. So let's start with first come first serve and from Monday. So with that, I'm going to end this lecture. Thank you to those who attended. I'm gonna stay like for 5 minutes after I end this. So if you have any questions, stay and ask using the Q&A. So with that, thank you, and hopefully talk to you on Monday. Bye-bye.